Now we are going to move on to the level 2 kind of question when you are in secondary 3, and that is pressure exerted by liquid. So what is the difference between solid and liquid is that your liquid can flow, and because of that you can use liquid to transmit pressure. Now what do I mean by that? So I'm going to give you a scenario. Now what would happen if I have a U-shaped cylinder that is with the same cross-sectional area between the left and the right? Okay, it is just a U-tube. Now what happened is that I put water into it, or liquid like oil. So I put liquid into it. What happened next is that I would actually, let me put this down. I would actually put a piston here, and then after that I put a piston here. Okay, and what I'm going to do is that I'm going to exert a force downward over here. Now when I exert a force downward on the left hand side, what would you think would happen on the right hand side? It would get lifted up, right? That is because two key points. Key point number one, your liquid would transmit your pressure from your left piston to the right piston, right? Now the second characteristic of the liquid that enables this to happen is because your liquid is incompressible. That means the volume is fixed. And because the volume is fixed, when I push down on one end, the other end would rise. Now can I do that with solid? I cannot, and that is because the third characteristic, and that is your liquid can change shape. Right? I can't do solid because the solid would not be able to change its shape, you know, and to accommodate the change in the column height. So this is quite straightforward, right? So the interesting thing about this, or how we take advantage of this situation, is that what if I am going to make the U-shaped cylinder now with different cross-sectional area, and I put the same thing. I'm going to put in a piston here, and then I'm going to put in a piston here. Now I'm going to put in some dummy value now. So AL, let's make it 1 meter square, and I have an AR which is 10 meters square. Now what I'm going to do is that I'm going to apply a force over here. Let's say I apply a force of 2 Newton to make things simple. I want to find out how, I know that this right hand side piston is going to go up, but I want to find out by how much force. Okay, we are going to try to do that, and I can calculate this because I know that my liquid is incompressible and that it is transmitting the pressure from left to right, right? Meaning to say, this force over here is going to generate a certain pressure in my in my liquid, and this pressure is going to be transmitted to the right hand side piston. So in another word, if I want to put this in mathematics, so let me erase this. If I want to put this in mathematics, it means that the pressure on the left hand side would be the same as the pressure on the right hand side, because pressure will get transmitted by my fluid inside this U-shaped cylinder with different cross-sectional area, right? And I know that my pressure is given by the force over area, and this pressure can be expanded similarly like this, correct? Now I can put in my values to see how it will look like. The force on the left is 2 Newton. The area on the left is 1 meter square. The area on the right is 10 meters square. And the force I want to find out is this. Now if I go and solve this, I would actually get Fr equals to 2 multiplied by 10. What you have seen here is that you will see that your force on the right hand side is actually equals to 20 Newton. Now, what does this mean? This means that we have amplified the force over here, the input force on the left, 10 times. Fr equals to 20, and that is what a hydraulic jack is. You use a very small force to lift up something that is very heavy. Then if you know this, you may be asking yourself, hey, I have just amplified 2 Newton into 20 Newton. What if I change the area here? What if I change the area here, not to 10, but to 1 million? Then my output force would be increased by a factor of 1 million. I can even create such a big force that I can reach the speed of light because F net is equals to ma. Oh my god, does that work? Now there is a catch. I want you to focus on the diagram that I have drawn on the left hand side. Now what happened, this is like an isometric view of the liquid column that is inside this U-shaped cylinder. Now when you apply a force on the left, what happened is that the liquid column on the left is going to go down. And it is going to go down by, for example, this amount. Let's say it goes down by D equals to, say, 5 meter, very deep. Okay. Now because liquid is incompressible, meaning that when this certain volume L has go down, that means my right hand column is going to rise by a certain amount that I do not know, but I know this volume because this volume has to come from VL. So basically this volume of R that rises up has to be equals to the volume of liquid that I have pressed down on the left. So I know that this cross-sectional area on the left hand side is 1 meter square. That's how I see here on the right. And down here AR is going to be 10 meter, right? Just now the dummy value we put in. So how do I calculate this volume? Well, the volume is given by the cross-sectional area times the height, right? So down here I would have AL times DL must be equals to AR times DR. What is A? L, that is 1. I give the input distance. I have used the 2 Newton force to press down on my left piston by 5 meter. Now this volume of liquid that I press down is going to reappear on the right hand side piston, right, to go up that much. Well, I know my AR is 10. Now I want to find out how much it will rise. Will it rise 5 meter? Well, let's see. I actually find out that my distance traveled by my right hand piston is just 0.5 meter compared to I have to press 5 meter. Can you imagine? 5 meter is how tall? From your house ceiling to the ground is about 3 meter. You press from, half a floor up from your ceiling, you press down all the way to the ground. That is the amount of distance 5 meter is. And then for the right hand side piston, it will go up by 50 cm, 0.5 meter. So there's a catch. Now, even if you have a hydraulic jack, you can use a very, very small force to produce a very, very huge force. The catch is you have to travel by a much larger distance on the left hand side, and the right hand side will actually move by just a bit. So I'm not sure whether you have seen this thing. Let's call this a wheel jack. So this thing, so a car is actually quite heavy, and if you have a punctured tire, you need to lift up the car before you can take out the wheel and change a new wheel in, right? So what happened is that they have this jack. What happened is that you just need to step on it, and when you step on it, a lot of time the car will get lifted up. Why? Do you think the amount of force you step on the jack is enough to lift up the car? No, right? But what actually happened is that this is actually a hydraulic jack. When you use your feet to press down on one cylinder, the other end of the cylinder will have enough force to lift up your car. But it will be just lifting up by just that tiny bit, which is not enough for you to take out the wheel. So what you need to do is that you need to step on it multiple times So for example, your feet, you lift it up and you press it down, maybe your feet would travel, let's say 50 cm, 0.5 meter, and you need to step on it like 20 times. So actually your feet has actually traveled like 5 times 0.5 or 20 times 0.5. That is like about 100 meter, and the car will be just lifted up by a bit. And that is the trade-off. You try to amplify your force, but you trade it off with the distance you travel. Now in the next chapter, when you learn this thing called conservation of energy, you will realize what happened here. And that is, for this hydraulic jack, there's also the conservation of energy. So I'm going to pause here, and we are going to now go back to the worksheet, and we're going to apply what we have learned here to the questions in your worksheet.